the stalest, most boring example that one can imagine. And that's why it's so wonderful, because it illustrates the idea with a minimum of fuss and calculation. And that example, which has probably been given billions of times, is I want to look at f of x equals x squared for x equals 1. So a quick picture. Here it is. And here's the point 1. And that's again p at 1, 1. And what I'm interested in is this tangent line. And I'm going to calculate the slope using the idea of derivative. And I think it's always a good idea to get some investment before you get into a problem. And so I would like to think about, when I get the answer, what are some things that should be true of it? Like, could the answer be that the slope of this thing is -7?
No, sir.
No, it couldn't. So I would expect it to be what?
Positive.
I would expect, this is my expectations, that f prime at 1 would be positive. And by the way, I wouldn't expect it, for instance, to be 100th either, would I? Because it's clearly not going to get that close to 0 when it cuts across. All right, so I've got some investment in this problem, and let's see what we actually get. What I need to do, I'll actually write it on the board again. I need to look at f of x plus h minus f of x divided by h. And that's going to be x plus h squared minus x squared, all divided by h. Correct? And that gives me x squared plus 2xh plus h squared minus x squared, all over h. And that gives me, the x squareds go away, gives me 2xh plus h squared, all over h. And please notice, this is the slope of these secant lines. So those were those green secant lines that you may remember from before. And for those, and a whole bunch of them. And those secant lines are all for h is not 0. So this h is not 0. So that's why I can divide by it. And in fact, when I do, the h goes away, and I come up with 2x plus h. That's the slope of the secant line. And now I let h approach 0. And when that happens, what happens to this expression here? It gets closer and closer to 2x, from which I can conclude that the derivative f prime of x is equal to 2x. And in particular, I said I wanted it at 1, so f prime of 1 is equal to 2. And that's it. Now, suppose I actually want to get the equation of that tangent line. The equation of that line, well, it's y minus 1 is equal to 2 times x minus 1, because it goes through the point 1, 1. And so I have y, let me do a little mental algebra here, y equals 2x minus 2 plus 1. So that's the equation of the tangent line. And let me just see if that agrees with my picture. If I let y be 0 to get the x-intercept, for y equals 0, I get 0 equals 2x minus 1, or x is equal to 1/2. And indeed, the picture suggests that that's about right. And while we're at it, let's just do a little bit more talking about this. What else can I say about the derivative from just looking at the picture, and of course looking at this too, maybe? other interesting things about the derivative. The derivative will be greater than 0 when x is greater than 0 because those tangent lines clearly have positive slope. It'll be 0 when x is 0, and it'll be negative when x is negative. And the picture says, yes, that indeed is true. In fact, you can say something else. As I think about these tangent lines to this parabola, what happens to their slope as I push x out? What? They get bigger and bigger and bigger. Does the equation agree with that? Yes. Get bigger and bigger and bigger. And moreover, by the way, they get bigger and bigger, but is there an upper bound to how big they get? No, they go, which says what in geometric terms? That those tangent lines are getting closer and closer to the vertical as you go out on this parabola. And of course, exactly the same thing happens on the other side, except negative. As you go out here, and I think this is a somewhat unusual way to say this, but I think it's useful. As you go bigger and bigger negative, the slopes become bigger and bigger negatively. So on the one hand, the mountain becomes steeper, and on the other side, the mountain becomes, the descent becomes steeper as you go up. So as you're climbing up the parabola here, it gets harder and harder and harder. And as you're coming down the parabola here, it gets easier and easier and easier.